Hello, this is Jeremy, and in this video I'm going to go through two examples of using the multiplication rule. One where independence does not apply and another where independence does apply. So when using the multiplication rule, you don't necessarily need to write the formula every time, but simply remember the idea of it. So let's take a look at how this multiplication rule would come up in this problem. So we're told a small school has 18 seniors, 27 juniors, 21 sophomores, and 30 freshmen. And we're going to randomly select two current students. Now it's implied we're going to select them without replacement. In other words, nothing here implies we're going to pick a student, put them back, and then go picking a student again. So usually you're looking for that phrase without replacement, but sometimes it's implied, like in this example here. And the first question is, what's the probability both students are freshmen? When I look at this, I really want to write out the formula the first time. And so when I see the probability both are freshmen, what I'm really thinking is this is the probability the first is a freshman and the second's a freshman. Now this isn't the only way to do it, but as far as using the multiplication rule, I have to think about it this way. And the multiplication rule says if you're finding an AND probability, you take the probability of the first event and you multiply it by the probability of the second given the first. So second freshman given the first as a freshman. Now this is the multiplication rule right here. This statement, this equality, this right here. This equation, this is the multiplication rule. And now it's about applying it to this problem. So the multiplication rule helps me with finding AND probabilities, but sometimes I have to read into it like I did here and recognize that it's an AND probability. Well, when I go to pick somebody, probably the first person is a freshman. Well, there's 30 freshmen, and then I got to figure out what the total number of students is. So we got 18, 27, 30, and 21. So this is the total number of students. And that's a total of 96. So this would be 30 out of 96, which can obviously be simplified, but just hold on a minute. And now we got to multiply this by the probability that the second person's a freshman given the first was a freshman. Well, think about it. We picked a student already, right? So there's only 95 students left to pick from. That's all based off of this. This is saying, hey, you picked a person, and not only that, the person you picked was a freshman. So how many freshmen are left? It must be 29. So this product is our answer. Now, of course, as with any probability question, it's 100% expected that you convert this to a decimal or a percentage, or at the very least, a simplified fraction. I'm leaving it like this so you can see where the numbers came from. But of course, you would say this approximately equals 0 point whatever that comes out to be. So again, notice the multiplication rule and probabilities, and I end up with a conditional. But since I don't have the numbers in front of me, like with a survey or something, I have to think it through a little bit. So let's try another question like this one. So in this question, it says, what's the probability one student is a freshman and one is a junior? Sounds very easy, like it's similar to part A, but it's a little more complicated than you would expect. One person's a freshman, one's a junior. Couldn't you end up with the first person a freshman and the second person a junior, right? That's totally possible. Or couldn't you end up with the first person a junior and the second's a freshman? And since we're looking at this as picking one at a time, essentially, wouldn't those both come out? So in other words, when I think about all possibilities, which is important when you're talking about probability, there's actually two ways this could happen. And both of these are AND events. First person's a freshman and the second person's a junior, or first person's a junior and second person's a freshman. So I actually have to use the multiplication rule twice, and I end up having to use the addition rule because of the or. So this will end up being probability of first freshman and second junior plus the probability the first is a junior and the second's a freshman. Now, why don't I have to subtract, right? Because the or statement implies I should use the addition rule, which is plus and then minus the and event. But it's not possible for the first person to be a junior and a freshman, so they're mutually exclusive, meaning I can just add. Okay, now I can go through, and instead of writing out the formula, I'm going to remember the process. Probability the first event, which is the first is a freshman. So we remember that this is 96 total students. And how many are freshmen? 30. Okay, and then I got to multiply by probably the second given the first. So it's saying the second is a junior given the first was a freshman. Well, there's 95 students left, and you picked a freshman first, so now you're picking a junior. There's still 27 of them left. Okay, and then it's plus, and now the same kind of process here. There's 96 students. What's the probability the first is a junior? Well, that'd be 27 out of the total. And then times, say you picked a junior first, what's the probability you pick a freshman now? Well, there's 95 students left, but you picked a junior first, so there are only 30 freshmen left. So whatever this comes out to be as a decimal or percentage would be your final answer. And again, I'm not simplifying here. So you got to be really careful with these and really analyze what are all the ways that these things could happen. So in the first example, it was a straight multiplication rule type of problem. Here was a multiplication rule problem, but you had that or involved. What else could come up? Well, a common question is something about at least one, at least one. And whenever I see at least one, I happen to think of the complement. So we talked about complementary events, or you've seen complementary events, hopefully. And so you know that the big deal with complementary events is the probability of an event A is 1 minus the probability of its complement. In other words, if A is really complicated, I can go figure out what a complement looks like and do 1 minus and find the probability anyway. Well, I claim at least one of these students is a senior is more work than I feel like doing. So if I want to find the probability at least one is a senior, I'm going to find 1 minus the probability of the complement instead. At least one is a senior means you could either have a senior and then somebody else, a freshman or a sophomore, etc. Or you could have somebody else and a senior, or you could have two seniors. So what's left out? No seniors, right? So probability that you have no seniors in your group. Okay, so this is 1 minus. That means the first person's not a senior and the second person's not a senior. So probability first is not a senior and the second's not a senior. So this would be 1 minus, and now I'm using the and, so I got to use a multiplication rule. The first is not a senior. Well, there's 96 students. How many of them are not seniors? Well, it'd be everybody except for these 18, right? So it would be 27 plus 21 plus 30, which is 78. So this would be 78 out of 96. And then times, well, if the first person picked as a senior, there's 95 students left, or excuse me, it's not a senior. And so probably the second's not a senior. Well, we already picked one that's not a senior, so it'd be 77. And so this calculation will give you your final answer. So we're using the complement here. Now I mentioned that there's two methods. The other method is actually to come back to this and calculate all three of these with the and multiplication rule, and then go through and add them up using the or, in other words, the addition rule. That can be very complicated. The more possibilities there are, the more complicated that becomes. Anytime I see at least one, I decide to use a complement. Much more straightforward, much easier typically than using the other method. Okay, so this is an example where we're sampling without replacement. But what about other things? What about when we have independence? So let's look at an example where we have independence. And so how would I recognize this? Well, in this example, we're told a printing company's bookbinding machine has a probability of 0.005, so very small, of producing a defective book. We're going to bind 3 books. So in other words, we're looking at 3 books. The chance of the machine messing up on a book is very small. And so we want to know that probably none of the books are defective. They all came out good. Well, this must be independent because if the machine was messing up specifically on one, dependence would imply since it messed up on the first, it has to mess up on the second. But the 0.005 is referring to a general random error type of situation. So this is an example of independent events. Book 1 being defective versus book 2 being defective. When I have independence, what happens is that the multiplication rule simplifies. So the multiplication rule was probability of A and B equals probability of A times the probability of B given A. But now I can say, well, if they're independent, probability of B given A is just probability of B. So in other words, I can multiply, and this generalizes to any number of events. So when you tell me the probability that none of the books are defective, and we're looking at 3 books, I can just multiply the probability that one isn't defective times itself 3 times. Probability that one is not defective is 1 minus 0.005 because defective and not defective are complements. In other words, 995. So this is 0.995 times itself 3 times. Of course, you would simplify this, right? But in the end, this is how the calculation comes out. So independence makes it where I can simply multiply the probabilities. Let's look at another question off the same example. I'm very familiar. What's probably at least one is defective? Probably at least one is defective. Well, this would be 1 minus the probability. And now I want to write the complement. At least one defective means either 1's defective or 2's defective or 3's defective. So what's left out? None are defective. In other words, this is 1 minus the probability non-defective, which is what we had before. So that's 0.995 cubed, 1 minus this probability. So in using the complement and the combination of them being independent, I'm able to find this probability. Okay, let's look at one more question that I could ask here. What's the probability all the books are defective? This is one that after seeing A, you should be able to answer. Because the probability the first is defective is 0.005, right? But so is the probability the second, and so is probably the third, and they're independent. So it's 0.005 cubed. So again, independence simplifies the multiplication rule in a very similar way that mutually exclusive simplifies the addition rule. In both cases, it's up to you to recognize whether you have that property or not and whether you can use it.